All right, so now we can use directed graphs to look like tournament play and like being able to determine the winner. And so we're going to kind of go through and kind of explore that. So one of the examples we talked about in the book was during the recent hotly contested season, the Chatham County Lacrosse League. Each of the 5 teams played the other 4 teams, resulting in 10 games. The results are found below. And so you got them listed out. So what they did, though, is to be able to represent this in a directed graph, they let the vertices represent the teams. And so we can see that, oops, sorry about that. There we go. So we can see that A would be the ants. And so we can see that the ants defeat the bats. So there's an arrow going from the ants to the bats. That means that they beat the bats. Ants defeat the sloths. So there's an arrow going from A to S. The ants lost to the robins. So that means that when we go from A to R, the arrow is pointing to A from the robins because the robins actually won. And the ants lost to the gnats. So same thing. If we're going from the gnats to the ants, is going to be an arrow going that direction and so forth. So we can use this to represent with directed graphs, and that you see that you have the initial vertex as the team that won versus the terminal would be the one that lost. All right, and so when each of the end competitors in the league play every other, the competition is called a round robin competition. Such a competition can be represented by a directed version of a graph called K of N, where the vertices are the competitors we directed from P to Q and so forth. And so this is essentially kind of like I was explaining in the previous examples. That's just called a round robin tournament. And so in a tournament, we define vertex P to be the winner if there's a Hamilton path for the graph that begins at P. So there's the catch-22 to this, is it has to be a Hamilton path. So remember, the difference between Hamilton and Euler is that Hamilton looks at vertices and Euler looks at edges. So we're looking at vertices to be able to do this. And so we want to be able to, each vertex is hit exactly one time. All right, so that means they would be the winner. So they have an Euler path. All right, so then this brings us up to Theorem 3. And Theorem 3, which we'll explore in the next slide, in a tournament graph with 2 or more vertices, there's always a Hamilton path. So we can find a Hamilton path. So the idea is that we want to be able to lay out that with each one being used exactly once. Sorry. Oops. All right, so here's Theorem 3 again. All right, so we have established that in every round-robin competition, there's at least one team that can claim to be a winner, namely the initial vertex of the Hamilton path that is guaranteed to exist. However, in our discussion of the Chatham County Lacrosse League, we saw that there were several teams that could make this claim. When do the results of the round-robin competition guarantee unique ranking of all the participating teams? That is, when are we guaranteed the tournament graph has a unique Euler-Hamilton path? Well, Theorem 4 will help us with that. So a tournament graph has a unique Hamilton path if and only if the graph has no simple circuits. So if we go back to simple circuits, no edge is repeated, and it begins and ends at the same place. So that's how we'll know that we'll have a unique. That's when we have a winner, is if that we have a Hamilton path where there's no simple circuits also. So let's take a look at our next slide. All right, so example 4. We have find a winner and ranking of competitors by finding a Hamilton path for the tournament graph. All right, so we're just looking for a path. So one particular path inside of this guy would be is that we can start at Q, we can Q be R, and R be S, and S be T, P, and P be T. And so we can see that that would be a simple path, a Hamilton path, because we're hitting all the vertices, and let's see, each vertex is hit exactly one time. All right, so that's a unique, that's a possible winner. So Q would be the winner because I can go from all of them. Okay, Because the graph has no simple circuit, so now determine whether the ranking is unique. So is that the only way we could do that, right? Is that the only possible winner? Well, let's see. Theorem 4 said that you had to have a simple circuit, all right? So let's go back and look at that real quickly. So Theorem 4 said a tournament has a unique Hamilton path if and only if the graph has no simple circuits. So a simple circuit is going to start and end at the same place and no edge is repeated. So when we look at this example, all right, determine whether the ranking is unique. Well, because the graph has a simple circuit QRSQ, so QRSQ, so my initial and my terminal is at the same spot, then we know that this is not a unique situation. And so indeed, we can find another Hamilton path. So we go and prove that. So we can also say that we have from R to S to Q to P to T. So there's another path that will get me. So where do we go? We did R, S, Q, P, T. So that's a path, right? And so there, we're basically saying at that point is that it's not unique. Let me hit pause for 1 second. All right, I had to go back and reread Theorem 4 again. So a tournament graph has a unique Hamilton path if and only if the graph has no simple circuits. And the reason we look at this is because what we're trying to do is when do the results of a round-robin competition guarantee unique ranking of all the participating teams? So a unique ranking means there's one first place team and there's one second place team and so forth. And that is when we are guaranteed that the tournament graph has a unique Hamilton path. All right. And so that particular theorem says is that a tournament graph has a unique Hamilton path if and only if the graph has no simple circuits. So when we go back to the next one, the problem is that we did have a simple circuit because we could go from Q to S to R to back to Q, or Q to R to S back to Q. So because of that, then we are wiping out the idea there's going to be a unique winner to this particular idea, this particular situation. All right. So kind of like, a little kind of befuddling, confusing, like why do we have these? These are just foundational pieces. I'm going to hit pause for just a second and make sure we've got all the slides. All right, so that's all. What you're going to do with this is you'll just be applying this and looking for paths, and kind of, it's not like nothing too complicated, just making sure you have these definitions written down in your notes so that way you can apply them and think about them and establish, so think about each definition and the examples of the theorems and so forth. All right, good luck with section 5.1.